Welcome to this video. My name is Mark Scythian. The date today is July 19th, 2024. The title of this video is Solid State Pumps, Mass Flow, Velocity, and Transistorized Control. So here we have essentially what is a limited moving part or parts mass flow controller transistorized control pump. So this is just a competitive flow control pump for various gases and liquids for high and low end applications in multiple industries. So again, when we're dealing with pumps, we have the potential energy, which could translate to the pressure, and this would split across into static and dynamic pressure. So when pressure is specified, it's often assumed that the type of pressure, dynamic or static, would be self-evident, but that has to be redefined because obviously the pressure involved with motion, or we could also equate it to a dynamic force of pressure times a cross-sectional area, but we do have a certain viscous or viscosity resistance, not just correlating with the fluid density, the rho factor, but also with the geometry of the pump, and specified backing pressure design parameters, which then stabilize a level of inherent static pressure. In other words, there's only so much fluid / gas or liquid that can move through a channel, and everything else would be a level of static pressure. So if we had something like a compressed gas charge subject to dynamic pressure or velocity discharge, we know that the static pressure is the only standing pressure until, let's say, the valve is opened and the static pressure drops, and the dynamic pressure then takes a registry into the metric. So we have to see the pressure as the potential energy and the kinetic energy as the velocity. We have the input side, so we'll assume this is the P1 on the input, and let's say we have a primary. We could move that over to probably the input side is the P1, and we'll say this is the output side, the P2. And again, we're dealing with the absolute pressure. So where relevant, if it was a liquid system, then we have an ideal fluid, and so only the hydraulic pressure would comprise of the overall absolute pressure. But if we're dealing with a gas, then we have to include the atmospheric pressure as well, call that ATM. So this is where we could split the Bernoulli equation across their equalities of KE and PE, we'll just call that 1 and 1, then having its equality to the output side, P2, fluid density rho v squared 2 plus rho GH2. However, we're going to have to figure out where we can cancel irrelevant expressions while still reaching an equilibrium point. So we have to then cut these two components out with respect to height. And then we have to include the continuity equation So whatever you were solving for, perhaps you were looking for a certain output kinetic energy or velocity. So that would be a practicality solving for its function. And so now, whatever the program or schedule is for the pump, whatever quality control or application, it's been ascertained that it could be just a discharge velocity of V2. So now we climbed a little bit higher. It depends on the materials that comprise the pump and not just the exterior casing, but the fundamental material science involved in the molecular dynamics of making a pump material. And this is not limited to just structures, but it's electrics, it's mechanical. It is the fundamental properties of the mechanical stresses, thermal stresses, etc., vacuum, expansion, contraction, expander, compressor, equilibrium dynamics. So we'll just call that, it's in the mechanical, it is in the electrics, which then splits down into our dynamic, and then also our electronic, electrochemical. So this is where we fall into transistorized materials. We could have a hybridization of materials that are partially structural as well as transistorized down to the molecular and atomic interaction and dynamics. So what we're doing is we're putting a material in that we could switch on and off many millions, tens of millions of times non-mechanically, so that the programming data, instead of having a bunch of mechanical components or physical components, we can just replace our hardware with SE software. So the design philosophy for at least the last 20 years with digital controls is parts or less, fewer parts, higher quality, loose tolerances, and software, let's just say SE, software heavy. So now you have fewer components, higher quality materials that are multifunctional, loose tolerances for programming criteria. You're able to serve different functions in a specific industry or industries who are relevant. And then you're able to also downgrade a system mass controller pump unit for a lower quality control industry. So this keeps the supply chain optimized while having minimal retrofitting, or we would say redesign. It could be taken out of an interchangeability with respect to the business and material side. But what is really important is that we're often looking at the whole pump, mass flow, velocity, and solid state / transistorized controllers on our mechanical / aerospace, and even automotive, combined with EE, electrical engineering, software engineering, and maybe to a lesser extent the process engineering, which we'll just call it chem. However, we have to take it up one more notch to the material science, called materials engineering. So materials engineering is going to deviate heavily more into the math and physics side. For which the physics side is going to break down more into physical chemistry, and this is then going to break down into various classical and quantum, we'll just say sciences, because one is going to deal with the particle and the other is going to deal with the wave frequency forms correlating into the, for example, crystalline structure, or even the fractals. So now we're going to move more into optics and fundamental photonic emissions, translating to the electrochemistry, thus making a programmable material. So materials engineering is going to take this up one notch above the standard mechanical, electrical, and even software engineering. And we could just, not necessarily, but keep chemical as the process engineering, and even systems and standards. You got to take it up to the materials engineering side. Then it really doesn't matter what you're working on. The ME and EE principles are fundamental, but coming up with a material that is intelligent, having mechanical, structural, electrical, electronic, thermal properties for which you could just implement a transistorized controller and then software engineer whatever function you want. So this was to be reprogrammed as a negative displacement pump and vacuum versus positive displacement pressure, then you could flip the numbers around and literally just take a negative V1 and solve for whatever variables that originally algebraically are arranged into the component cluster. But however, once you identify your constant, you'd have to take it out, whatever that is. And because you're having essentially a function, it more likely is a rate of change derivative that mathematically translates itself into the function, and then it could code up into the software parameter. So you have to make a design schedule so that programmability license to an operation is serviceable to the client or the market. But the main takeaway regarding mass flow, velocity, and just the general pump designs, whether they are mechanical, analog, electrical, digital, solid state, etc., is the understanding that fundamentally we're dealing with pressure as potential energy, velocity is the kinetic energy, and then if you visit the Bernoulli equation, you see that the first rho GH is going to be correlating to mgh, or potential energy, on the input side, along with the output side, rho GH2, and conversely the 1/2 rho v squared 1 is going to correlate from the input side to the 1/2 rho v squared 2 on the output side. So now we do have irrelevant expressions that find themselves in equilibrium that we can just cancel out. But once you find these parameters on input and output potential energy, you have the understanding that we still have the input and output velocities, for which you have a substitution potential depending on if you're crossing or inverting, either or. So that depends on what's going on with the function of this pump. But other than that, and the methods to devise a fundamental parametric design for potentials and limitations on a pump design, mass flow is the actual mass and potential energy on the P side, and velocity is just the displacement energy regarding the motion. So this will correlate to the mass will correlate to the current. We're assuming this will be a DC current, and the velocity would be correlating to the voltage. Again, we're assuming it's DC. Not that microinverters could be implemented for rectifying AC to DC at a much micro or nano level, depending on the pump's innovation. So these are the basic takeaways of developing a purely electronic solid state transistorized control fluid pump. And then the last point is to keep mindful of the material's density of the fluid. So that is a gas or a liquid, its density flowing through the pump. Thereafter, we have other factors such as the flow coefficient, the type of material, and the fundamental molecular resistance of the gas or liquid / fluid flowing through the pump's structures, then correlating to the dynamic viscosity. So in wind tunnels, that whole dynamic viscosity controller is artificially controlled by having a degree of freedom on the temperature. So wind tunnels can do things like artificially heat and cool the airflow to some extreme temperatures so that Reynolds number scaling is accomplished. So you have to also take the RE number into consideration, and the 3000 point is the transient, greater than is the turbulent, and less than is the laminar. So that is just the difference between the density of the fluid and the inertia. So when you turn on a faucet, on a sink very, very low, you see just about a transparent water stream. Obviously, there are now visible impurities. On a atomic level, there may be many impurities, but they're not readily visible. The light will pass right through the stream of low discharge water. So this is said to be in density. But when you turn on the faucet full force, you see a clouding effect. You don't see transparency, as the molecular interaction is now very chaotic and turbulent. So now the fluid has reached inertia. So these factors have to be wrought out at that transient point. So in your physics classes, those fundamentals you could start applying into the solid state transistorized control units for pump mass flow and velocity. So at the very end of this, there may be just one tiny metering pin or solenoid that has extremely finite values to open and close the output flow, reacting to temperature, pressure, the Reynolds number, and dynamic viscosity changes as different demands induce or curtail different functions of the overall algorithm. So this is just one of many, if not millions, that can mesh into the final CS control system, which then opens and closes the pump to some very, very, very tiny controls of molar mass. So there are some pumps that are in the micrograms per square centimeter on the flow cross-sectional area, and micrograms per cubic millimeter on the discharge. So it depends on the standard and system, but I'm making a point here. It isn't necessarily the units, but it is the finite hydromechanical behavior meshing with near consistency to the electrochemical behavior of the transistorized materials. And the purely informational and electromagnetic behaviors of the software algorithms. So this information is becoming energy, becoming matter. So this obeys the entire correlation of matter, energy, information, and may theoretically then fall under thermodynamics law 0. But not necessarily, as this is a zero pressure metric for absolute reference point. So again, this is not just about pumps, but this is about meshing control systems, having a correlation and a translation. So ergonomics and market competition reaches optimized states in safety, reliability, life cycle, cost, ergonomics, are very programmable. and of course the quality control and the quality assurance, repeatability, and the ergonomics could also fall under the retrofitting if need be. And then of course you have the liability. So the asset exceeds the liability. So again, if you're dealing with a learning curve with pumps, especially solid state transistorized pumps, flow controllers, gas and liquid velocity applications, software, electronic, and transistorized control systems all mesh into one. These can be derived through the fundamentals of physics, chemistry, and applications. So putting them all together and seeing the big picture based on fundamentals is a good start. Organizing the planning sequence and schedule can make these systems come together. So whatever your focus is, you can make that contribution to the overall system. But those who want to go to a higher level above the fundamentals of engineering as a standard, we say M, E, and EE, and their applications and related technical disciplines like aerospace, automotive, CS, software engineering, etc. They want to take it up a notch to much heavier math and physics with many abstractions starting at molecular dynamics and moving more into the quantum and photonic applications, atomic applications, quantum geometry, etc. Then you take it up a notch to the materials engineering, material science. So all of these are relevant, but it's going to start at the material side and spill down into the MEEE side and then into applications. So if you take a little deviate or take a little break out of the standard and start getting into the actual materials and their molecular and even atomic quantum functions, then putting these systems together is far more practical, because if any improvements are made in an industry, or let's say gas turbine engines, or anything that has a huge potential for breakthroughs, all of that can be modeled, can be calculated, can be proven, but nothing's going to happen till one starts to play or research or jump into the materials engineering world. So thank you for watching this video and have a great day.